don't have the pen for this today, so when we're going over it, I use the whiteboard. But here is your very first question. Just going to be what is the CPI increase for each of these things. Do one at a time. The first one is branch, second one is memory. Go to 047. Just answer A immediately, and then when you're done with calculating the branch CPI increase as well as the memory CPI increase, then change your answer from A to B.
What was the number?
047. I see that not a lot of you are done quite yet, but in the interest of time, I do want to get through two of these questions and still have time for register renaming. So do talk to the people around you and work together. Or if you are done, you can go over it. And then when you are done with the peer discussion, change your answer from B to C.
No, this is the thing. So this is just some things. And then we got L1 penalty, 5%. That was the penalty, 1.5. And then the next one. This would be L2, which is 1.5%. The penalty of accessing main grid, which I got to do one.
Like 05 times 2.
Because 105 is the L1 problem, and then the penalty for missing L1 is having to access L2 in 50 seconds.
Key help us, I think.
That's on me, yeah. 7.3, which is at 1.5. Gosh darn it. This is what's gonna ruin me on the exam. 1.5 plus 1 is 2.5. Gosh darn it. That's an example of 3 plus 2 on the exam. Because I can't do basic reading comprehension.
Yes.
I understand. Like,
Oh, so like it's easier.
yeah, but then it's just can't read.
That's what I'd be going back for that. Okay. They're pretty big ones. I think we're only here, right? So, so we're pretty almost 15, you know, it's. I have no, we have 15 years. Yeah. feels like you're constantly doing nothing.
And you don't hear as much discussion. Unfortunately, you have changed your answers to C. So let's go over this together. The first question I have is, how many of you guys have watched the lecture recording for Wednesday? And then since that has the explanation of the setup, and then we can just skip to the shortcuts. Do you want me to go through the setup again? Because some of you guys have not watched that. Okay, let's do setup then. So a question like this will show up on the exam. So what is CPI?
Cycle per instruction.
Number of cycles? Over. Number. Right. So here. And let's ignore the 1.1 for now, okay? If I have a perfect pipeline processor, no problems. Number of instructions is just going to be instruction count. Yes?
Yeah.
What's the number of cycles? Everything's perfect.
Instruction count plus 4.
Instruction counts. 5 stage, 4 cycles still is yes, but instruction count is in the billions, right? So let's just call it instruction count, right? So if you're perfect, instruction count divided by instruction count, CPI is 1, right? But we're not perfect in this case. You would get 0.1 probably from maybe 10% of instructions incur a 1 cycle stall penalty. So this is just instructions. What percentage of them are affected? What is the penalty? This is the number of cycles of those penalties, right? Does this give you the total number of instructions that have that penalty? And what is the penalty? And the total number of cycles, right? And then instruction count cancels, right? So your shortcut to get to your CPI increase is just to calculate this part. You don't need to go through this whole process and cancel instruction counts. But for this, let's do this whole process. We'll do branch next. So this is how I was just going to add in that 0.1. Okay. But you could go straight to just, it's just 1.1 to start with. So branch. First thing I need is
Instruction count.
Yep, I'm starting with instruction count. What do I calculate next?
The percentage of instructions that are branch.
That's the total number of branch instructions. So 20% of instructions are branches, right? So 20% times instruction count. This is the total number of branches. Okay. And then someone else, what's next? After I have the total number of branches, what do I need? So mispredict of what percentage? 0.05. Okay. And what does this give me?
The miss rate.
The 0.0. This is the. So this is total number of branch instructions, right? Instruction count times 0.2. Then total number of branch instructions times miss rate gives me.
All the branches are missed.
Yeah, all of the instructions that gave me a miss. And then what's my penalty? 1 cycle. And I'm just gonna continue this on down here. This is my branch CPI increase. Memory CPI. What do I start with?
Instruction count.
And you from? Because I know you understand. I want someone else to give me these answers. So instruction count. Then what? What is next? What are the other pieces of information that I have? Mhm. And what is the global miss rate?
3%.
Yeah, but what are what's on top, what's on bottom? How is it calculated? What is miss rate? What does it mean? Okay, Chris?
So we're looking at the L1, L2, so then we do similar to the first part, we would do like the L1 for IC times the L1 global miss rate
Yes.
times the number of cycles.
Yes. Okay. So global miss rate is total number of misses to that cache divided by instruction count. Okay, so if I multiply it's 3%. 0.03. 3% of my total instructions have a miss to L1. So then this is my total number of instructions that miss to L1. What's my penalty? This is increase because of L1 misses. And what do I start with? Instruction count. What's next? Zero point zero zero %. Global miss rates. This is. And then what's my penalty for accessing the main memory? Okay. So then this would be instruction count. This cancels, 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 cancels. Right? So you would have 1 plus 0.1 gives us 1.1 for the base CPI with the hazards. Okay. This is my CPI increase due to branch mispredicts. This is my CPI increase for missing from L1 or missing from L2. Add this and this, that's my CPI increase for memory instructions. So what is this?
0.01.
This is 0.01. What is this?
1.5.
1.5. What is this?
One. This is one.
Just one. So then. CPI is 1 plus 0.1 plus 0.01 plus 1.5 plus 1. So what is this?
3.7.
Okay.
Oh, was it 3.61? My bad. I'm sorry.
Right. We all understand how to do this question? confident? And do study guide with this information now, study, we'll be able to do it, not this coming Monday, but the next Monday when we have the exam. Right? Yeah. And like I said, a question like this will show up, for sure. That. This is your other question that I will guarantee this style of question will show up on the exam. You need to be able to fill in these pipeline diagrams. You need to know forwarding. You need to know how to show those stalls on the diagram. We're currently on answer C. Oh, we don't have time for this. Let's just go over it real quick. Okay, pipeline diagram. What goes on top of my pipeline diagram?
The instruction and the number of cycles.
Cycles. Right? Cycle 1, 2, and then here is the instruction, right? So add. Right? What happens in cycle 1? Fetch the add. Next is level. Cycle 2, what happens to the add? And what happens to the local? Cycle 3. What is? Have another add. What happens to the first add? What happens to the lower? We have a problem. Yes or no?
Yes.
Yes.
What is this writing to?
Zero.
What is this reading from? Huh? When is T0 going to be available? After here, right? When is it needed for here? Right here. No problem, right?
No.
I want you guys to be confident. Okay? I know you were confident. Because not everyone was. Okay? So, but what else does that mean? Well, what happens here? Right? Here?
Yeah.
Okay, so now this with
Draw the arrow.
forward. Right? What happens here? And then so. What does that do? Cycle 5. What happens to my add? What happens to my lower? And do we have any problems?
Yes.
So. What does this one do?
You bubble the decode and then you do it again.
What else happens?
Yeah, you bubble some as well.
And then. Redo. Right? Cycle 6. What do I do here? Right back. This is going to. And now I have the data. Right? What does this do? Cycle 7. What do I do here? photo here. Do I have any problem?
Architect, so forwarded and fixing UA.
Do I even have a problem?
No, you don't. Doesn't have to write.
But so. Execute. Cycle 8,
Right back.
right back. Memory. Cycle 9,
Right back.
right back.
Processor.
And we're done. So key things are, we need to show forwarding. We need to show stalling properly. You bubble the one that is going to be redone. Because this is the stall, this is the one that's actually the decode, this is the real fetch. Okay, so I need to log in, get the presentation ready. There is a survey on Yaza for you guys to fill out to give feedback. And then there's more content in the slides, so you can, along with the study guide, do those questions as well. Yeah, Chris.
You can access the form. You said it's no longer accepting responses.
I need to just change that. There you go.
People of that. You have to confirm to continue.
Why- okay. Please, where is download? Me out of
You have
here.
to do save as. And then download a copy. Not my preferred way of doing it either.
I have 5 minutes to spare, so. We can fight with technology. So my group members. For some reason, the camera points and tracks someone else, so we don't have the whiteboard recording.
Oh, no.
That's fine. Slideshow. There you go. Alright, so. Thanks all you guys for the next 15 minutes.
Yeah.
Okay.
Alrighty. Good morning, everyone. We're Team One. My name's Matthew.
I'm Ellie.
And Kabir. All right, and we're gonna be going over the section for renaming registers. Is it a touchscreen to go to the next slide or
Just hit the arrow key or space.
the keyboard?
So this is the roadmap for our presentation. We're going to talk about what is register renaming. We're going to talk about a little bit about the history, where it's used. In our papers, specifically talking about superscalar processors, which are processors that have multiple execution units. We're going to talk a little bit about out of order execution, why it's used, particularly to prevent false dependencies. And then we're going to talk a little bit about how it's implemented. What is register renaming?
Just dismiss that. Dismiss all. Yes.
Register renaming is a technique of storing temporary renamed registers into a buffer. Basically, it abstracts away physical into logical registers. Usually implemented in conjunction with shelving. A queue or buffer for instructions that check for dependencies. and sends instructions out when there is no longer an instruction issue. And then by eliminating the need for in-order instructions, the number of instructions executed per cycle, IPC, increases, which is something separate from CPI. But yeah, this introduces false data dependencies, like right after write or right after read. And then in the paper, it talked about partial renaming and full renaming. So partial renaming only uses some instruction types. For example, the Power One only had one floating point unit. And then there's full renaming, where all instruction types use register renaming.
And the reason it matters is that the Power One only had one floating unit is that it couldn't do anything out of sequence because there's only one unit to process the data. So it doesn't have parallel processing. You can't do multiple instructions at once. So it doesn't run into the same problems that register renaming really solves.
And then a little bit about the history. Precursor was Tomasulo's algorithm. But due to the complexity, it wasn't adopted quickly. Beginning in 1992, full renaming started to appear in high-end models. And then at the time of writing of the paper, it was considered to be the standard feature of performance-oriented superscalar processors.
So with the register renaming, you have the partial renaming where you only have a few operands, and then the full renaming, which is all operands, but it's also separated into things called static and dynamic register renaming. Static being where it's done on the compilation level, and dynamic being where it's done in hardware. So with that Power One, it was done in hardware with the Tomasulo's algorithm. But for this, where it's used, we're going to using ILP, which is instruction level parallelism. We kind of did that with the advanced pipelining slide of, I think, a week and a half, 2 weeks ago in the lecture things, where you get more out of instructions completed per cycle. I kind of stole this from Justin's slide over here, where the dependencies will show up. With the parallelism going on, you're going to have out of order instructions having multiple instructions being completed at the same time, where these false dependencies will show up where they weren't in a regular MIPS single cycle, is when you have two instructions going on the same time, then starting to have only their temper, like you only have 32 bits of registers with MIPS. So it's going to have some complications at each stage for this. And that's where we want to really use these register renamings to help eliminate this so that it just keeps running smoothly and you don't get these cycles being stalled. Next slide. So I have a little basic example just to give you an idea of the two different types of data hazards we'll have here, which is right after write and right after read. Where I have just basic two adds. You have the add RO, R1, R2, and then you have add RO, R3, and R4. If that's both running at the same time, when we get to the execute part, we're going to show that all those, the two ROs are going to be writing to the same register. Which one's going to be the one that gets the register? But if we do a little bit of renaming, if you go to the next slide. Yeah, if we just logically take the idea of, it doesn't matter what the register name is. They're going to be two different values, and we just have it variable A and variable B. We can keep the pipeline running without stalling and having a problem of which register it goes to. And we just rename the register because it doesn't matter, or it doesn't matter if it's register 0 or another available register. The other one would be right after read. It's the same idea. You have add R0, R1, and then R2, but then the next instruction is add R2 to R1 and R3. In a single cycle, we have no issue. It just moves through kind of with the example we just had previously. But with if they're both running at the same time, you're going to have R2 also being written and the execution of the R0. So which R2 value gets added to R0? Then that's why if we, this slide was an old version of the TO, should be RO. But if we change the one of the register renames and change it to a different variable or a different register, you no longer have that issue, and then it moves along smoothly. We can go to the next slide. Yeah, so as I said earlier, Mitchell only has 32 registers. So if you have a large amount of instructions and you're trying to do this parallelism, you're gonna run out of room using your same temporary values for it. So it's okay to do register renaming to have it be an available register, or if you do different types of register renaming where you have like a buffer or something, you can utilize that to keep the pipeline running smoothly. The next slide, please. Yeah, and just there it is. I fixed it in this one. So it's the same idea. You still have the R0, but then the add A with the R2 gets to just be renamed, and both instructions can go through the pipeline smoothly without stalling or there being any data hazards from both instructions executing at the same time.
Right, and so we prepared a larger example to make it a little more obvious that it doesn't really matter if you want to tackle this from a in order perspective or a parallel perspective, but I decided to go out of order. So the first, if you look at the instructions, you got a load word that loads to R0, you got an add that adds R0, R4, puts it back into R0, and then you store that R0 in a memory location. And then you follow that up with a multiply that takes R6, R7, stores that in R0, then you store that R0 value also in memory. And when you look at it, you see a bunch of dependencies. And let's say the load word's taking too long, we don't want to do the load word first. Can we do a different instruction first? So when you rename these registers to look at like what the dependencies look like, so you look at that after renaming, the load word, I renamed R0 to A. And that same R0 value is used in the next instruction as a operand. And then we get a new R0, that's my B now. And then you store that in the instruction 3, you store that B value in the memory location. And then you look at instruction 4 and 5, it's taking those two registers 6 and 7, stores it into a brand new value R0, that's C. So if you take a look at it, you will find that the first 3 instructions are kind of dependent on each other, but the last 2 instructions are completely separate from the first 3 instructions. So if you wanted to do this out of order, let's say that load word's taking too long, the processor can fetch that multiply instruction, complete that multiply instruction, and then instead of storing it in R0, it can store it in like a reorder buffer or a temporary register file which we're going to talk about in a second. You can essentially do these out of order, or you can do them at the same time and kind of have 2 separate R0 values at the same time and keep track of which one you want to use for each instruction. And these are the 4 types of implementations that were explained in our PDF that we got. Is that the first one going left from right, you can see a merged rename and architectural register file. That just means that they made a bigger register file, so maybe they allocate 16 registers normally, and then they say, okay, we have 8 rename registers. The second one is just a standalone register file where you keep those, it's physically separate. There's the 16 registers in one register file and then a separate register file physically for the 8 temporary, let's say. Then there's also reorder buffers and then shelving buffers. And these were the arrows down below show you where they've been used in the last, well, not the last 10 years, between the 90s and 2000 essentially. So register renaming, it uses the merge architectural and rename register file. Sometimes it employs a standalone rename register file like you saw. It keeps the rename value either in a reorder buffer or sometimes shelving buffer. When I saw they don't do these, I have not seen any where they had multiple implementations at once. They only typically just use one. And I believe that's the.
And now, we now stand open for questions or points of clarification. Go back a few.
Yeah, I think.
This is a pretty hefty topic, and it kind of utilizes a lot of the stuff that we'll see from some of y'all's presentations as well. So if we glossed over a few things like shelving or.
I think a big one is like some of the false dependencies we talk about right after write, right after read. Those are not things that really occurred in our in sequence processor. That's something, yeah, for MIPS. That's something that seems to really come out when you do things out of order or in parallel. Any questions?
Questions?
I have a question. So for the example, you guys are you guys only renaming the dependent registers? Because I see R4, R5, R6, R7, R8 are still not renamed.
Correct, yeah, no, we're only,
There's no problem with those ones, so there wasn't really a need to rename them. But if we had reused those registered names or numbers, if there was like a dependency, we would rename those as well. We were just trying to get like a very baseline example. So you could see like, oh, if there was like one register where there was an issue rather than trying to do like 3 different registers that have issues. Because you could handle multiple registers that have issues and then figure out which dependencies are real dependencies, which dependencies are false dependencies, and then like rename them and then store it in like something like a reorder buffer and then pull the value that you want. Because essentially, like I said before, there's more than one value of R0 here. So like if when you do an instruction, it's got to ask which value of R0 do I want? Do I want the R0 value that was gotten from that add, or do I want the R0 value that was gotten from that multiply?
and the reason we won't rename everything on top of that is that this still takes time. Later on in the paper, they talk about like design space and rename rate. And that all takes time. That all takes cycle time. So you only really want to rename things that are actually a false dependency. So if there's no dependency, you don't have to put it in the buffer. You don't have to add a tag to it. You don't have to add the hardware if you're doing it dynamically or more time compiling it with the static. You just want to do the thing to keep the pipeline moving without stalls.
The other thing to keep in mind is you don't want to rename a real dependency.
Right.
Yeah.
Yeah.
Rename a real dependency, then your program's behavior changes, you'll have incorrect code.
Mhm. That is the dark side of that. If you make a mistake, you're gonna have nonsense.
Okay, so.
That was, I like.
Again.
Pardon?
Oh,
Is this that? Right, so this
Showing
slide,
up during your lecture stuff, Justin. How do we stop it?
it's because I opened Outlook.
Okay.
I opened Outlook. So this slide, just for all of you guys to know, is a really good example of why we need register renaming, how it's helping us, right? It's getting rid of those false dependencies. It's reusing R0, but really that R0 is not the same data, right?
Mhm.
So we only have that one physical or virtual, I should say, virtual R0 register, right? In MIPS, we have 32 virtual registers based on the ISA. But when you actually make an architecture for MIPS, you might want 64 real physical registers, or maybe 128 real physical registers, because that gives you this flexibility of getting rid of these false dependencies, because the compiler only knows that there's 32 virtual registers. Right. Okay.
That's 1450. So if no other questions. Cool.
Yes, good.
Thank you, everyone.
Thank you.